In section 111, section 11, chapter 1, we're going to be looking at what's called LU factorization. In the last section, we looked at elementary matrices, and we saw that if we have a matrix A, then we can rewrite it as a product of elementary matrices, which each elementary matrix is a matrix that performs a single elementary row operation. So if we find out what row operations it takes us to put A in reduced row echelon form, or convert it to the identity matrix, then we can write A as the inverse of the first elementary matrix times the inverse of the second one times the inverse of the third, and so forth. Well, it turns out that if we were to just put A in row echelon form, remember row echelon, we have pivots, and typically we get ones in those pivots, but you don't necessarily have to have ones in those pivots. And then usually there are numbers above the pivots, zeros below it. And that's what we called an upper triangular matrix. That's upper triangular. Well, typically it takes a number of elementary row operations to get A in upper triangular. So if we were to take those elementary operations that took us to get to row echelon form and multiply those together, then those would give us a lower triangular matrix where we have pivots and then zeros above the pivots and numbers below. So what we're going to do to begin with in this section is to rewrite a matrix as a product of a lower triangular matrix and an upper triangular matrix. So let's look at an example of that. And we're going to, in this section, when we put our A in our matrix in row echelon, we're not going to require necessarily there to be ones on the diagonal. There may be, but we're not going to necessarily require it. And one thing that you'll find out about LU factorization is it's not necessarily unique. Depending on how you put it in row echelon form, depending on what you want your pivots to be, there are different combinations of LU sometimes that will multiply to give you your original matrix. But just real quick, I'll read theorem 1. The product of lower triangular matrices with ones on the diagonal is a lower triangular. If we multiply two lower triangular matrices, we get a lower triangular matrix. If we multiply two upper triangular matrices, we get an upper triangular matrix. So let me find an example to work through. Let's take the matrix 1, 4, 6, 2, -1, 3, 3, 2, 5. And let's put it in row echelon form, or at least reduce it to an upper matrix. So conveniently we have a 1 here. So let's begin by taking the second row and getting a 0. So we want our second row, we need a -2 here, so we're going to take -2 times the first row plus the second row, and that's going to give us our new second row. Our new third row, we're going to take -3 times the first row plus the third row, and that'll give us our new third row. So our first row, we're leaving the same. If we do a -2 times the first row plus the second row, we get a 0, -8, -9, -12, -9. We do -3 times the first row plus the third row, we get -3, and 3 is 0, -12, 2 is -10, -18, 5, -13. Now, for convenience, we could convert that to a 1 there. It's not completely necessary. So let's just leave it like it is, and let's convert this to a 0. So to get a 0 here, we would need to have a +10 here. So our third row, to get a 10 here, we would multiply that to get by a -10 ninths. Notice we want a 10. To get rid of that 9, we divide by 9 so that the 9's cancel, and we have a 10, but we need that to be positive, so 2 negatives make a positive. So that times the second row plus the third row will give us our new third row. So our first row stayed the same. Our second row stayed the same. Our third row, if we do -10 ninths times a 0 plus a 0, we get a 0. -10 ninths times that gives us a +10. -10 is 0. And then here, if we do that times -10 ninths, we get our 10 -13, so -3. So notice here, we have an upper triangular matrix. So if we go back to look at our other ones, this elementary row operation, we did -2 times the first plus the second, so the inverse of that would be to add 2 times the first plus the second. That's occurring on the second row position, so the first row and the third row are not changing, but on the second row, we're doubling the first row and adding the second row. This is our second operation, so that's e sub 2. We want the inverse of that. The inverse of this would be in the third row position to add 3 times the first row plus the third row. So the first and the second row are unchanged. On the third row, we're doing the opposite of this, so a +3 on the first, or 1 on the third. And then this was our third elementary operation, so the inverse of that, that's applied on the third row, so the first and the second stay the same. In the third row position, we're affecting the second and the third, so the first is the same. The inverse of this would be a +10 ninths and a 1. So if we take, so A, we can get from taking the inverse of our first elementary times the inverse of our second elementary times the inverse of our third times our upper. And if we've done this correctly, when we multiplied multiply those together, that should give us our lower. So let's take those 1 0 0 2 1 0 0 0 1 times 1 0 0 0 1 0 3 0 1 times 1 0 0 0 1 0. Sometimes I have to say it out loud so I can remember it. So if we multiply these together, this should give us our lower. So let's just multiply the first two together. So this row times this column, we get a 1, 0, and 0. This row times the second column, we get a 0, and a 0. This times the third column, we get a 0. And the second row times the first column, we get a 2, 0, and 0. Times the second column, we get a 0, a 1, and a 0. 0, 0, 0. We multiply this times the first, we get a 0, 0, 3. 0, 0, 0. 0, 0, 1. Now, to finish our lower, multiply that. Comes here, and just quick point. Our theorem that I read earlier said if we take lower triangular matrices with ones on the diagonal and multiply them together, we get a lower triangular matrix with ones on the diagonal. Notice this is lower triangular with ones on the diagonal, lower with ones on the diagonal. When we multiply those, we get a lower triangular matrix with ones on the diagonal. We multiply that times this one, we have ones on the diagonal. Both of these are lower, so our result here should be lower triangular with ones on the diagonal. So if we multiply here, we get a 1. This times the second row, we get 0. Times the third row, we're going to get 0. We can use our theorem and say, well, we know that our diagonals are going to be 1, and it's lower triangular, so now we can just go back and multiply to get these positions. So this one comes from the second row, first column, so second row, first column, we have a 2, 0, and a 0. This is third row, first column, so third row, first column, we have a 3, 0, 0. Third row, second column, so 0, 0, 10 ninths. So if we did that correct, that should be our lower triangular matrix. Now, yes, it is a lower triangular matrix, but we want one such that LU equals A. So to check that out, let's multiply what we have and see if that really gives us A. So our lower times our upper, which our upper, let's see, where was our upper? This was our upper. So 146, 0, negative 9, negative 9, 0, 0, negative 3. So let's multiply this out and see if that really gives us A. So first row, first column, 1. First row, second column, 4. First row, third column, we have a 6. Second row, first column, we have 2, 0, 0. We have 8 to minus 9 and a 0, so minus 1. 12 minus 9 is 3 and 0. And then we have 3, 0, 0. 12 10 ninths times negative 9, that's negative 10. So 12 minus 10 and 0. 12 minus 10, I believe, is 2. Third row, third column, we have 18. 10 ninths times negative 9, again, that's negative 10. 1 times minus 3. So 8 minus 3 gives us 5. Now, I guess the test is that A? Been so long, I can't remember what A is. So A, 1, 4, 6, 2, negative 1, 3, 2, negative 1, 3, 3, 2, 5. 3, 2, 5. So yes, this is the proper LU factorization of A. Lower triangular, upper triangular. So again, just a quick review. We'll take our A and we'll use elementary operations to get A into row echelon. So get row echelon, which we didn't completely put it. I guess I should be careful when I say we're to put it in row echelon where we're not requiring zeros on the diagonal. So I guess it's not row echelon, we just row reduced it and put zeros below the diagonal. So I guess I should be careful with my terminology. Then after we get our upper matrix, then our lower is just a product of the inverse elementary matrices that it took to get our upper. Now, let's use LU factorization to solve a system of equations. Let's suppose we have the system of equations x1 plus 2x sub 2 equals 1, 2x sub 1 minus x sub 2 equals 7. And let's write this in AX equal B. So A is our coefficient matrix, 1, 2, 2, negative 1. B is our vector of the right side. Take A and write it as a product of lower and upper matrices. And then let's do that. And then we'll come back and see what we're going to do after that. So let's take an aside and let's take A and find its LU factorization. So if we've got 1, 2, 2, negative 1, then to get this as an upper, we need a 0 here. So our row 2, we can change by doing negative 2 times the first row plus the second row. So if we take negative 2 times this plus that, we get a 0. Negative 2 times 2, negative 4, negative 5, and we're leaving the first row alone. So notice that's our U. That's an upper triangular matrix. So our lower comes from our inverse elementary matrix C's, there's only one of those in this case. So we did that on the second row, so our first row stays the same. Our second row, we're doing the inverse, so instead of doing a negative 2, we're doing a positive 2 on the first row, or 1 on the second. Notice that's lower triangular. So our L is 1, 0, 2, 1. And again, if it took more than one row operation to get to our upper, then it would be a product of those elementary matrices. So our LU is 1, 0, 2, 1, 1, 2, 0, negative 5. So that's actually equal to 8. Alright, so we said we're going to take the system AX equal B, and we're going to change A to LU. Now, let's start by doing a little substitution. Let's call this Y. So let's say change this to LY equals B, where Y is just a vector. Notice if we were to take, remember that X is just your variable vector. So if we were to do U times X, we would do this times that, which if we do a 2 by 2 times a 2 by 1, we get a 2 by 1, which Y is a 2 by 1. So this is another system of equations. L, Y, and B, where B, what was our B? 1, 7. So let's remember what this is saying. This, if we were to multiply row 1 times this is 1y1, 0y2s, so y1 equals 1. If we were to multiply this times this vector, 2y1s plus 1y2 equals 7. Well, notice since we only have one number in this first row, that tells us what y1 is. y1 is 1. Well, we can back y2 out of that. If we substitute a 1 in for y1, so 2 plus y2 is 7. Subtract 2, so y2 is 5. So y is the vector 1, 5. Now, what we're looking for is x. Now remember, ux is what we changed to y. So u is 1, 2, 0, negative 5 times x, and that's equal to our y. So if we look at this, 1, if we multiply this out, 1x1, 2x2s would give us 1. We multiply this out, we get no x1s, minus 5x2s is 5. So that tells us that x sub 2 is negative 1. We can substitute back in x sub 1, 2 times minus 1, so minus 2 equals 1. So x of 1, therefore, is 3. So x is 3, negative 1, which is what we were looking for. We were looking for what values of x satisfied our system of equations. So that takes a little bit of thought, but the convenience about using L and U is when we put L times Y equals B, then having only one number in this row, that immediately gives us Y1. Then the next row has two values, y1 and another. So we know what y1 is, we can use that to find y2. If we had a third row, now we would know y1 and y2. We can plug those in and find y3. So knowing y, if we substitute, so this was y, so since ux is y, then u times our x is our y. Notice our second row only has one number in it, so we can immediately find out what x of 2 is. Our next row has two values in it, one of them being x of 2, so we can immediately plug in what x of 2 is and use that equation to find x of 1. If we had three equations and three variables, then our bottom row would only have one, so we would use that to find our x of 3. Our second row, let's just write that out, we would have some number, so we could immediately find x of 3. Our next row would have an x of 2 and x of 3, but now that we know x of 3, we're going to plug that in to find x of 2. Then our first row, now we would know x of 3 and x of 2. We could plug those in to find x of 1. So we can use LU factorization to solve a system of equations. Now, one catch here is we must be able to find LU without doing what's called a permutation. And a permutation means that we swap rows. For example, in order to put this in, to reduce this matrix to an upper, we would have to do a permutation. We would have to swap row 1 and row 2. Because we have a 0 in the first pivot. And to get an upper, we can't have a 0 in the first pivot, so we would have to do that. So, in order to use LU factorization to solve our system of equations, we can't have that. So we have to manipulate our system of equations before we begin. Now let's look at an example of a matrix that, as it stands, cannot be put in LU factorization without doing a permutation. So in that case, we do what's called, instead of A equal LU factorization, we do PA equal LU factorization, where we do a permutation on matrix A to put it into a matrix that does have LU factorization. So let's begin by doing a permutation here on this matrix. Let's put this as our first row, so let's swap row 1 and row 3. So if we do that, we get this. Right now we're leaving the second row where it is, and the third row becomes this. So our elementary matrix that does that permutation, we swapped row 1 and row 3, so row 1 would come here, row 3 here, and we left row 2. That's called a permutation matrix. Remember, the inverse of a permutation matrix is itself. So if we want to continue row reducing this, we would need a 0 here, so we would need a -2, so our row 2 we would get from doing negative 2 times our first row plus our second row. So negative 2 here makes a negative 2 plus 2, so 0. Negative 2 times this, that gives us a 4. Minus 4 is 0. Negative 2 times 5, that's negative 10. 7 is negative 3. And right now we're not changing the other ones, because we already have a 0 here. Now notice we have a 0 here. We don't need a 0 here and a number below it. We need these swapped. Our next pivot needs to be here, so this row needs to move up. So we would need to swap rows 2 and row 3. So our permutation for that, so our second permutation, we're swapping row 2 and row 3. So row 2 would go here, row 3 here. Now keep in mind, we've done multiple permutations. So we could actually come up with a permutation matrix that is the combination of both of our permutations. Our first permutation and our second permutation. So let's do that real quickly. So our permutation matrix. The first permutation, we swapped rows 1 and rows 3. Our second permutation, we swapped rows 2 and 3. So our permutation matrix, if we multiply those out, we get a 0, 0, 0, 0, 0, 0, 1, 0, 0. This one times the first, we get a 1, a 0, and a 0. This one times the first, we get a 0, times the second, we get a 1, times the third, we get a 0. So let's go back. We could do our permutation matrix times our original A to get into something that can be put into LU form. So our permutation matrix times our A basically puts our first row in the second position, our third row in the first position, and our second row in the third position. If you want to multiply that out real quickly, you can do this times the first column, and that gives you a 1. This times the second column, this times the third column. Notice that puts your third row on top. And multiply the second row, that puts your first row here, and then your second row will be here. Now let's see, let's put that, so that's our PA. Now let's row reduce that, so we need a 0 here, so our third row, we're going to do negative 2 times our first row plus our third row. So our first row is staying the same, our second row is staying the same, our third row we did negative 2 times the first row, Negative 2 times this, that's 4. Minus 4 is 0. Negative 2 times the first row, negative 10 plus 7 is negative 3. Notice that's a u. So after we did our two permutations, which we actually combined into a single permutation matrix, we converted our A, when we did P times A, into something that when we row reduce it, can become an upper. And in this case, it only took us one step to get that upper. So we need to find our lower, so our elementary operation, which there was only one of those, that's the inverse. We need the inverse of this. So the inverse of that, we're doing that on the third row, so our first two rows stay the same as our identity. Our third row, we do the opposite of a negative 2, so a positive 2 on the first row, and then our third row once. Notice that's a lower. So our LU factorization is 1, 0, 0, 0, 1, 0, 2, 0, 1 times our upper, so that's LU, but we have to be careful because when we multiply that out, that does not give us A. That gives us P times A, because A was not, as it stood, was not able to be row reduced without doing permutations into an upper triangular. So when we multiply that out, that's going to give us PA. 1, negative 2, 5. 0, 2, 3. 2, negative 4, 7. If we were to check that, we were to do this row times this column, we would get a 1. This times this, we get a negative 2, 0, 0. 5, 0, 0. This row times this, we get a 0. This times here, we get a 2. This times the third one, we get a 3. This one times the first, we get a 2 and a 0. This times the second, we get a minus 2, a 0 and a 0. I'm sorry, that's a minus 4. This times the third, we get a 10, 0, minus 3, which is 7. So if we're going to use this LU factorization to solve a system of equations, A, we either have to find LU that equals A, or if we can't reach our upper without doing permutations, then we have to do permutations on A and then put it in LU. So in our case, we had to do two different permutations on A in order to get it into an upper. So once we did our permutations on A, that gave us a matrix that we could reduce to an upper. And of course our lower came from our elementary matrix, the inverse of it. So that's doing LU factorization on a matrix that requires permutations. So let's solve a system of equations that involves finding PA. Let's look at the system where we have A as 0, 2, 4, 1, negative 1, 2, 0, 3, 2, and B has negative 1, 2, 4. So this is a system AX equal B. We're looking for what values of X will make this true. What does X1, X2, X3 need to be so that when we substitute those in for our X's, in this equation we get minus 1, for this one we get 2, for this one we get 4. Now, we want to eventually use LU factorization to do this, but notice in A, we're going to have to do a permutation. We're going to have to swap these two rows. So we're going to have to do a permutation on A to get it to where we can do LU factorization on A. But notice if we do a permutation on A to keep our equation balanced, we also have to do a permutation on the right side. If you think about what's going on here, if we have a system of equations, this row goes with that number, this row goes with that number, this row goes with that number. So if we come in and we swap rows 1 and 2, then we also have to swap rows 1 and 2 on the right side so that we keep the correct pieces of the equations together. So let's do our permutation. Let's swap those so that we have 1, negative 1, 2, 0, 2, 4, and we're going to leave the bottom row where it is. PA. So our PB, we swap the first two rows on the left, so we have to swap the first two rows on the right. Now, essentially at this point, you can just think about this as a new system. You can think about this as A, this as B. So let's solve the system that involves this coefficient matrix and that vector. So let's take our left side and let's put it in LU factorization. So we have zeros here. We need a 0 here. So our third row, we would need a negative 3 here added to that to make this 0. So if we have a 2 and we need to change it to a negative 3, we need a 2 on bottom, so that goes away. And we need a negative 3 on top. So we're multiplying that second row times negative 3 halves and adding it to the third row. So negative 3 halves times 2, the 2's will cancel. Go ahead and write the first row, it doesn't change. The second row we're not changing. The third row we're taking negative 3 halves times this plus that. Negative 3 halves times 2 is negative 3 plus 3. The negative 3 halves times 4. The 2 and the 4 reduce, so that gives us negative 6 plus the third row, so that gives us negative 4. So that's our upper. Our lower comes, notice we only had one elementary row operation. So our lower comes from the inverse of that, which the inverse of that we're doing on the third row. So the first two rows are just our identity. Our third row, we're affecting on the second and third position, so the first position stays a 0. The inverse of subtracting 3 halves would be to add 3 halves of row 2 and then row 3. So that's our lower, and that's our upper. So our AX equal B, our A, after we did our permutation, we did change A to LU. So remember that we group U and X together and do a substitution. We call U X Y. So we're going to do LY equals B. So we're going to use our lower. That's our lower. Our new B, remember, was 2, -1, 4. So we're going to use L and B to find Y. So Y1, no Y2s, no Y3s, so Y1 is 2. No Y1s, Y2, no Y3s, so Y2 is -1. And then this bottom equation says that 3 halves of Y2 plus Y3 equals 4. Well, we know that Y2 is -1, so -3 halves plus Y sub 3 is 4. Or Y sub 3 is 4 plus 3 halves, which 4, that's 8 halves, plus 3 halves, so 11 halves. So we use the lower triangular matrix with B to back out values of Y. Once we get Y, then we reverse substitute. UX, that's Y. So U, let's take this. I don't want to rotate that. So that's our U and our Y. So we can use our U and our Y to find X. So notice our bottom row, no X of 1s, no X of 2s, minus 4 X of 3s equals 11 halves. So if we multiply, if we divide by -4, X of 3 is -11 eighths. Then we go to our second row. 2x of 2s plus 4x of 3s equals -1. We know x of 3. So 4 times -11 eighths. So that's -11 halves. So add that to both sides. So positive 11 halves minus 1, so minus 2 halves. What's that? 9 halves divided by 2 is 9/4. So now we have x of 2 and x of 3. So x of 1 minus x of 2 and 2x of 3's, that's equal to 2. So x of 1 minus 9/4 plus 2 times x sub 3. So 2 times x sub 3 is minus 11 fourths. So that's minus 20 fourths, which is minus 5. Add 5 to both sides, 1 equals 7. So not the prettiest of numbers, but not every system has quote-unquote pretty numbers for solutions. For time's sake, I'm not going to go back and plug all those in, but if we were to take those solutions and substitute them into our original system of equations, x0, x sub 1s, 2x sub 2s, 4x sub 3s, that would give us negative 1. 1 x sub 1 minus 1 x sub 2, 2 x sub 3s, that would give us 2, and so forth. And just to check, I did, when I paused the video, I did come over on the side and check those out, and that did work. So the only thing that we haven't done that's in this section is to do LU factorization of a matrix that's not a square matrix, but you treat it essentially the same. The only difference is that your upper and your lower, let's see, let me just read this theorem for you. LU factorization for non-square matrices. If A is an M by N matrix, and let's say we can reduce A to row echelon without doing any permutations, then we can come up with a lower triangular matrix with 1s on the diagonals. That's M by M. So the lower is going to be a square matrix. And we're going to have 1s on the diagonals. But the upper is not going to be square. It's going to be rectangular. Notice if we do LU, we have an M by N and an M by N. Those are the same, so we can multiply those, and the size that we get is M by N, which is what A is. So we're going to do the same type of thing. We would take A and we would row reduce it until we had an upper triangular, which we could have that. If we have more rows than we have columns, then we're going to have at least one row of zeros in there. If we have more columns than rows, then one of our rows is going to have a pivot and then another row in it. So just once we get into an upper triangular, notice both of those are upper triangular, then our lower we're going to get the same way we have in the past. It's going to be a square matrix that comes from our row operations, our elementary row operations.